Hello, my name is Roy Simpson. I'm a professor of mathematics at Cosumnes River College in Sacramento, California. Welcome again to Proofs in Differential Calculus. In this video, I'm going to prove the lemma, the limit as theta approaches 0 of sine of theta over theta is equal to 1. And before I prove this, I want to show that this is true through a justification. And the justification requires us to replace the letter theta with x. So I'm going to take a look at sine of x over x and look at how both those functions, sine of x and x, how they grow as x approaches 0. Now what you're looking at here is a Microsoft Math calculator. And we're looking at the sine curve. In fact, let me go ahead and zoom out a little bit so you can see. The blue curve is a sine curve, and the green curve is y equals x. So we have sine of x and y equals x. And as we zoom in, get really close to x equals 0, here, you see my x values now range from negative 0.5 to positive 0.5. Let me zoom in even further. Now my x values range from a negative 0.125 to a positive 0.125, or a negative 1/8 to a positive 1/8. You see that both curves match up almost exactly. In other words, for very small values of x, sine of x and y equals x look almost exactly the same. This is very important in the proof because it basically is telling us that for small values of inputs, the sine is roughly equal to x. So for small theta, sine of theta is approximately equal to theta. And of course, if sine of theta is approximately equal to theta, then their division, or in other words, their quotient, right, is going to be 1. Their ratio is going to be 1. Now, of course, that's not a proof, so let's go ahead and do a proof here. For the proof, it's going to require us to use a very complex-looking figure here. So let me write proof in here. And this complex-looking figure is just a unit circle. In other words, this point right here is 1, 0, and this point right up here is 0, 1, right? And we'll go ahead and label some of these other points, and I'm not really going to go crazy with the labeling. I'm just going to maybe call this A, we'll call this B, we'll call that point at 1, 0, we'll call that C, we'll call this D, and the point at the origin we'll call O. That seems pretty good labeling of letters here, or of points, sorry. And now we're going to compare lengths. And I know that this is going to be kind of weird looking. I know it's got to be kind of weird looking. So let's go ahead and talk about the logic of what we have in front of us. The first thing to note is that since this is a unit circle, in other words, the radius is 1, and if we call this angle theta, well, on a unit circle, the arc length that we cut out is going to be the same as the angle, right? That's by definition, by definition, a radian measure. So if we're talking radians, the arc length that gets cut out here is going to be the same as the angle theta, as long as we're working on a unit circle. So the arc from B to C is equal to theta. That's an important part of this whole entire process. Now, using that, maybe I'll use a different color so I can show you. The sine of theta here, the sine of that theta, is going to equal opposite over hypotenuse, right? This is a right triangle. So the opposite would be length AB, in other words, the magnitude of AB over hypotenuse, which is 1. So in other words, that's just the magnitude of AB. However, we should be able to agree this length from A to B, that's actually less than the length from B to C. That's a pretty easy argument, right? That length, that chord length from B to C has to be a little bit greater than the the leg length from A to B. And of course, that chord length is going to be slightly less than the arc length from B to C. The arc length from B to C, which we've described as theta. Okay, so that's an important statement. Mainly because it's telling us that the sine of theta must be, in this chain of inequalities here, sine of theta must be less than theta. If I divide both sides of this inequality by theta, theta is positive in this case, so it doesn't switch inequalities. So this implies, and maybe I should have put my implication sign there too, that sine of theta over theta must be less than 1. Okay, so we know that we have a bound on sine of theta over theta. It's going to be less than 1. It's actually possibly going to be equal to 1. It just depends on what theta is. Now what I want to do is I want to make a tangent, or I'm sorry, now what I want to do is make a lower bound for sine of theta over theta. And to do this, I am going to first of all draw in a tangent line to this unit circle at the point B. Let me go ahead and do that. So there we have a tangent line to the unit circle at the point B. And notice where that tangent line intersects the line CD, right here. I'll call that point E. Why not? So I have A, B, C, D, and now an E. That's kind of important for the next part of this proof. So what we're going to do, and maybe I'll draw this in, or write this in green, okay? One thing we should know is that the arc length, let me write that in here, the arc length from B to C has to be less than, if you look at this arc length from B to C, it's got to be less than the length from B to E plus the length from C to E. So it has to be less than the length from B to E plus the length from C to E. Okay, if you look at that, it's got to be true, right? Here's the length from B to E, here's the length from C to E right here. That's got to be greater than the arc length from B to C. And of course, that distance, B to E plus C to E, has to be less than the distance from D to E plus C to E. So let me write that in as well. Just had to find my pen here. Yeah, less than C to E plus D to E. And of course, a faster way of writing that is just the length from C to D. What's interesting about that length, C to D, is that you can relate it, in a way, to the tangent of theta. So maybe I should write that over on the side here so you can kind of see it. The tangent of theta is opposite over adjacent, right? Opposite could be considered this red line from C to D. Over adjacent would be from O to C. Or in other words, that length CD is the same thing as the length from the origin to C times the tangent of theta. Okay, and that's important here, so let me switch back to green for pen colors here. So this is equal to the length from the origin to point C times the tangent of theta. However, this is a unit circle. So the length from O to C is a length of 1. So this is the same thing as 1 times the tangent of theta. And of course, tangent of theta is sine of theta over cosine of theta. Now we're going to get into what this means. The implication of this is that the arc length from B to C that we have right here has to be less than sine of theta over cosine of theta. But we've already said right at the beginning, the arc length from B to C is theta. So this implies that the arc length from B to C, which is theta, must be less than sine of theta over cosine of theta. Now I'm going to go ahead and multiply both sides by cosine of theta and divide both sides by theta, and you'll get the following. Cosine of theta has to be less than sine of theta over theta itself. Now we have this restriction, this bound on sine theta over theta. The bound is as follows. Let me write it down on a new sheet of paper here. We know that the cosine of theta is less than sine of theta over theta, but sine of theta over theta is less than 1. So we have a function that bounds our ratio from below and a function that bounds our ratio from above. Well, the limit as theta approaches 0 of the cosine of theta is going to be 1. In other words, as theta approaches 0, cosine of 0 is just 1, so okay. And another thing to note is that the limit as theta approaches 0 of the right-hand side of this triple-sided inequality of 1 is just going to be 1 because it doesn't rely upon theta. So let's see, I have continuous functions here. The left-hand function is a lower bound. The right-hand function is an upper bound for the middle function. And as theta approaches 0, the left and the right-hand functions approach 1. So by the squeeze theorem, or you might have heard the squeeze theorem as the sandwich theorem, they're called the same thing. By the squeeze theorem, the limit as theta approaches 0 of sine of theta over theta must also approach 1. QED. Now, of course, the graph that we drew a little bit earlier is a little bit easier to see. This one right here, you could easily see the ratio, or you could easily see that the sine curve and y equals x look exactly the same as you get really close to 0, so their ratio should be 1, but that's not a proof. This is a proof.